Hello students, welcome to this module, which is part 5 in our series on differential equations. In the previous module we discussed the use of eigenfunction expansion, or what is sometimes called the finite Fourier transform, to solve ordinary differential equations. Okay, this was done in the previous module. Today we will extend this idea to a partial differential equation. Okay, as you know, partial differential equations are linear partial differential equations are often solved using the method of separation of variables. Okay, but as I told you, the method of separation of variables has its basis on eigenfunction expansions. So we would like to refer to that as either the method of eigenfunction expansion or what some textbooks refer to as the finite Fourier transform. Okay, so we will of course illustrate this with the help of an example so that you can understand the method very clearly. We will try to solve a partial differential equation in one spatial dimension and one time dimension. At first, okay, let me first write down the equation. This is an example from heat conduction, unsteady heat conduction. Okay, T is a temperature and small t is time, capital T is temperature. This is the spatial coordinate. Okay, now this is like you have, let's say you have a bar, x is equal to 0, x is equal to let's say L. Okay, and this bar is uniformly transforming or losing heat outside, which can be modeled using Newton's law of cooling or using a heat transfer coefficient, and that will be linear in temperature itself. So this represents heat loss to the surroundings. Okay, and let's say there is also another term that is like a source or sink term. This represents either internal heat generation or internal heat loss due to some reaction or something like that. Okay, so you may have an electrical heater which generates heat. So let's make the problem as general as possible. So this is the problem. Of course, this is a partial differential equation, and we have to supply two boundary conditions because it's a second order partial differential equation. We'll keep the temperature at x is equal to 0 to be 0 and temperature at x is equal to L also to be 0. As I noted in the last module, you can have t is equal to t naught, and then you can define t minus t naught as the new another new variable, let's say theta or something like that. So instead of going through all that, I'm just assuming the temperature itself to be this is at all times. Okay, now at initial condition at time t equal to 0, temperature at all x at time t equal to 0 is given by a function q of x. Okay, and this q of x is such that it also satisfies q of 0 x equal to 0 0 and q of x equal to L is 0. So you have some initial temperature distribution at time t equal to 0, and after time t greater than 0, you just maintain the temperature at 0 at at these two boundaries at all times, right? And that's how. And then we want to understand how we want to find how temperature evolves as a function of x and time, the unsteady evolution of temperature. Okay, so this problem is well specified. It's a linear partial differential equation. Okay, now if you look at this partial differential equation, now I'm going to consider an operator like this. I'm going to consider this as my operator, and I'm going to call this operator as L. Okay, so L of phi is nothing but d squared phi by dx squared minus u squared phi. Okay, now I want to solve the eigenvalue problem for this operator. The method of eigenfunction expansion relies on the solution of an eigenvalue problem. Now I will leave it to you to show that this is a Hermitian operator. Okay, and or a self-adjoint operator. Okay, so I will not prove this. You can prove it yourself based on the methods that we have, and you have with respect to Dirichlet boundary condition, phi of 0 is 0, phi of L is 0. Okay, so let's solve the eigenvalue problem for this operator. The eigenvalue problem is L phi is lambda phi. Okay, now L is nothing but d squared phi by dx squared minus u squared phi is lambda phi. Okay, let's keep it as minus lambda phi, okay, for convenience. Okay, so d squared phi by dx squared is equal to, if I take this u squared on the other side, I'll get minus lambda, minus of lambda minus u squared operating on phi. U squared is some constant parameter. It's not a function of x. It's a given constant. It's like the heat transfer coefficient or some dimensionless representation of the heat transfer coefficient. So, and lambda is the eigenvalue, and phis are the eigenfunctions that we are going to solve for. Okay, I want to define this variable lambda minus u squared as sigma. So I will solve the eigenvalue problem as d squared phi by dx squared is equal to minus sigma phi, where sigma is this. Okay, now with phi of 0 is 0 and phi of L is 0. Okay, this eigenvalue problem has been solved already, and you know what the eigenvalues and eigenfunctions are. So the eigenvalues are sigma n will be n squared pi squared by L squared, and the eigenfunctions are signs, but sigma n is nothing but lambda n minus u squared. That means lambda n is u squared plus sigma n. Instead of sigma n, I'm going to put n squared pi squared by L squared. So these are the eigenvalues. N will go from 1, 2, 3 and so on. Okay, this is something that we have solved before as well, so I don't want to spend time in again solving this eigenvalue problem. Okay, right. So the eigenfunctions phi n of x are root 2 by L sine n pi x by L, n goes from 1, 2, 3 and so on. Okay, this is n pi. Okay, now we have to go to the original PDE that we are interested in solving, is L of t, because L is the operator partial squared by partial x squared minus u squared. Okay, L is that operator. L of t plus f of x, this is a given function, is equal to 1 over kappa. This is like the thermal diffusivity. Okay, so we multiply both sides by, we are going to take the inner product of the entire equation with phi and the eigenfunctions of this eigenvalue problem that we just solved, and integrate the entire equation like this. Okay, so I'll go term by term, 0 to L phi n of x L of t dx plus 0 to L phi n of x f of x dx is equal to 1 over k integral 0 to L phi n of x partial t by partial time dx. Now imagine that our unknown is temperature T, right? So we are trying to expand T as summation, right? Some Tn of T times phi n of x. See that temperature is a function of both x and time. We have solved an eigenvalue problem in the spatial coordinate x and got eigenfunctions which are orthonormal. So I can expand any function of x in terms of those eigenfunctions, but the coefficient of expansion will become functions of time because you're expanding a function of two variables x and t, and only x is getting expanded here. And if this is the case, then Tn of t will be simply integral 0 to L, right? Tn of t is integral 0 to L This is like finding the Fourier coefficients given the function. How do you find the Fourier coefficients? Using orthonormality. So if you know Tn's, you can find T of xt, but the definition of Tn of t itself is just this, okay, because this is useful when we do this expression, simplify this equation here. Now L is a self-adjoint operator. This means that integral 0 to L phi n L of t dx is integral 0 to L t L phi n dx. Okay, that's the meaning of self-adjoint, because the boundary terms vanish. U L V is L U V. Okay, so that means that what I have here instead of this, I can now write 0 to L, right, T phi L phi n dx. Okay, now but L phi n is nothing but minus lambda n phi n. So the first term out here will become integral 0 to L t of xt minus lambda n phi n dx. That's the first term. Now this lambda n is a constant independent of x, so I can pull this outside, minus lambda n 0 to L t of xt phi n of x dx. But if you know what is that, this is nothing but, this is the same. This whole thing out here, is nothing but Tn of t. So this is nothing but minus lambda n Tn of t. The first term in this simplifies to minus lambda n Tn of t. Now let's look at the second term. Let's look at this term. Now if you expand any function in this eigenfunction basis, because f also satisfies f should also satisfy the same boundary condition, then we can expand f in terms of these eigenfunctions, and if I do the integral, I'll get the coefficients of that expansion. So I can call this nothing but fn. Okay, this is not a function of time, so it's just fn. Okay, so this is just fn. The second term will give you only fn. Now let's look at the third term. On the that is the term on the right side. Now here t is time, partial t is a function of only time, and the integral is only over x, so I can write this as 1 over k partial t of integral 0 to L phi n of x t of xt. Okay, Now this is nothing but Tn of t. Okay, that is from again from the definition of Tn of t. So this equation out here will become, this equation becomes, let me rewrite it in terms of the simplified form, right, minus lambda n Tn plus Fn plus 1 over k. Now the partials will become, this was originally a partial derivative, this will become an ordinary derivative now, because this is a function only of time. Tn is a function of only of time, right? So I can write this is equal to 1 over kappa dTn d time. Okay, or I can rewrite this and in this fashion, plus lambda n Tn is equal to Fn. This is a first order ODE in time for Tn. This is a first order ODE in time t, small t for Tn. Can be easily solved. This is of the form dy by dx plus py is equal to q, which we know how to solve. So Tn of t is Fn by lambda n plus Tn0 kappa t. Just verify that this is indeed the case. Okay, after simplifying, after using the integrating factor, you will get this. Now what is this? What is Tn at time t equal to 0? This is Tn at time t equal to 0. Okay, now how do you find that? This is, we know what is the initial condition. T of x at time t equal to 0 is given to us to be some q of x. Okay, so if I were to expand this in the same eigenfunction basis, right? If I were to Tn of x, t of x at t equal to 0 is q of x, is nothing but summation qn phi n of x. Okay, now this will be the expansion coefficients of, the expansion coefficients will be these qn's. So qn's will be Tn at time t equal to 0 is nothing but 0 to L. How will you find this? Again by orthonormality. T of x at time t equal to 0 phi n of x dx. Okay, that is qn, and that qn is nothing but, this is the same thing that occurs here. Okay, so this is known to us. Okay, so once the initial condition known, this is the initial condition after all, you can take the inner product with phi n to get either Tn at time t equal to 0 or what we call qn. Okay, this is qn. Okay, so now the solution Tn of t is nothing but Fn by lambda n plus qn minus Fn by lambda n e to the minus lambda n kappa t. Okay, this is the solution to this differential equation in terms of Tn's of t, right? So, but we are not interested in Tn of t, we are interested in t of xt, but that is simple because that is nothing but, we originally started off writing t of t sorry about this. Yeah, here you see this. Once you know Tn, you have to do the summation to find t of xt, right? So t of xt is n is equal to 1 to infinity Tn of t phi n of x. What is Tn of t? That is directly from here. You have to substitute this whole expression here, and we know what these individual quantities are. Fn is nothing but 0 to L f of x phi n of x dx. Qn is 0 to L Q of x phi n of x dx. Lambda n's are the eigenvalues, which are u squared. We just derived this in the first few minutes of this module. L, and the eigenfunctions are root 2 by L sine. Okay, so once we have all this, we can write the solution as to the original PDE as a summation over n is equal to 1 to some large number, which depends on the accuracy to which you want the solution, fn by lambda n plus qn minus fn by lambda n e to the minus lambda n kappa t. Okay, times phi n of x. This is the solution using the method of eigenfunction expansion, or what you may call finite Fourier transform. Now as t goes to infinity at large times, right, all these terms will decay because all the lambdas are positive, and you have e to the minus lambda, so you will get what is called the steady state limit or the steady state solution, which is t of x, t tending to infinity, time tending to infinity, is nothing but summation n is equal to 1 to infinity fn by u squared plus n squared pi squared by L. Okay, okay, times phi n of x. Now this is what we already solved in the previous module for the steady state problem, and the unsteady state solution as time t goes to infinity should obviously agree with the steady state solution we derived. So if you look at the previous module, we had just solved the steady state solution for this problem. Okay, so that's how one solves a partial differential equation with one spatial and one time coordinates. Okay, now let's do another example wherein I'm going to do a partial differential equation in two spatial coordinates. So this is the example is laminar flow in a rectangular duct or a channel. Okay, so imagine you have a channel like this. Let me draw a rectangle first. Okay, sorry about this. Okay, so this is the channel in which fluid is flowing in this direction. Okay, okay, now this is the x coordinate, and I'll call, okay, let me just write this. This is the x coordinate and this is the y coordinate of a Cartesian coordinate system, and z is in this direction, the flow is in the z direction. Okay, now let's call this as x is equal to a and this as y is equal to b. So let's imagine the channel going from minus a to a, and x is equal to minus a to x is equal to a. This is x equal to 0, and similarly y is equal to minus b to b. Okay, so that is the the width and height of the channel. Okay, and of course in the boundary conditions in fluid mechanics is that u of x y is 0 at x is equal to a, and at x is equal to b. These are the no slip conditions. Okay, I'm sorry, I have used a slightly different coordinate frame, so let me stick to that. I'm calling this as x is equal to 0, and I'm calling this as y equal to 0. Okay, so the coordinate is fixed exactly like this. Okay, instead of like this, it's fixed like this. Okay, okay, that's how I place the coordinate system. So x, y, z, this is 0, x equal to 0, x equal to z, the bottom is y equal to 0, y equals b. Alright, so you have, these are the boundary conditions. There is no initial condition because it's a steady state problem. The problem we are going to do is just a steady flow. So let's write steady laminar flow. So the governing Navier-Stokes equations, and then we are assuming unidirectional flow. The flow is only in the z direction. Will now reduce to mu times partial squared u by partial x squared plus partial squared u by partial y squared is equal to partial p partial z. Now if the flow is in the positive z direction, the pressure gradient must be negative. So I'm going to write dp dz as minus delta p by L, where this is a positive quantity. Okay, now therefore, and let's call, now let me rewrite this, plus partial squared u by partial y squared is equal to minus delta p by L mu, and I'm going to call this combination as alpha. Okay, so alpha is a positive number, therefore the equation will finally simplify to is equal to minus alpha, and use the z component of velocity because the flow is only in the z direction. Okay, so now we have to use this is the problem with Dirichlet boundary conditions at both the boundaries. So we have to figure out eigenvalue problems out of this. So let's consider the operator Lx of u is partial squared u by partial x squared. Okay, now if I consider this, the original equation becomes, right, the original equation was partial squared u by partial x squared plus partial squared u by partial y squared is minus alpha. So partial squared u by partial x squared is minus partial squared u by partial y squared minus alpha. Okay, so I'm going to call this as Lx. So Lx u is minus partial squared u by partial y squared minus alpha. So I'm going to solve the eigenvalue problem for Lx phi is equal to minus lambda phi. Okay, and x is between 0 and and phi of 0 is 0, phi of a is 0, and once we solve this, the same eigenvalue problem that we have solved before, so n squared pi squared instead of L in the previous problem, we have a squared, where n is 1, 2, and so on, and phi n of x is the normalized sinusoidal functions, and so on. Okay, so once you solve this eigenvalue problem, what I next do is, so any function f of x can be represented as which obeys the same boundary conditions as phi n's, that is the Dirichlet boundary conditions, fn times phi n of x, where fn is nothing but integral 0 to a f of x phi n of x dx. Okay, so now we had Lx u is minus partial squared u by partial y squared minus alpha, right? Now I'll multiply, I'll take the inner products on both sides, I'll multiply by phi n and integrate between 0 and a dx of the entire equation. So you'll get 0 to a phi n Lx u is equal to 0 to a, on the right side 0 to a minus partial squared u by partial y squared phi n minus 0 to a alpha phi n. Okay, there is dx everywhere, so if I forget dx, please include that when you take your notes. Alright, now this is a self-adjoint operator, so phi n Lu is nothing but 0 to a u L x phi n dx. That's on the left side. On the right side, I can pull out partial squared by partial y squared, because the integral is only with respect to x, which becomes u of x y phi n dx, and alpha can also be pulled out. Okay, now this object out here is nothing but un of y. You have x, this is the coefficient of expansion of u of xy. Suppose I take u of xy and expand in an eigenfunction expansion, only in x, then the coefficients will be functions of y. So this is that coefficient un of y, right? So if I were to do this integral, okay, this will be some number, because this is just integral of sine n pi x by a, right? So the answer for this is root 2 by a alpha. Alpha is of course multiplying the whole thing, root 2 by a, okay, times a by n pi, sorry about this, a by n pi times, okay, this is some constant which I'll call a n because it's a function of n. Okay, so and this is un of y, and what is L phi n? This is nothing but minus lambda n phi n, and lambda n goes outside because it's a constant, so it will become u phi n dx. This is nothing but minus lambda n un of y is minus, this partial will become ordinary because this is a function of d squared by dy squared of un, okay, plus, so I'm going to call this entire thing as an, including the negative sign. So this, I'm going to write this as an, okay. So I'm going to call this, including the negative sign is also included in an, right? So I can now rewrite this as d squared un minus lambda n un is an. Okay, so first we did the partial differential equation after doing one round of eigenfunction expansion has now been reduced to an ODE in Y. Okay, now this ODE in Y can also be solved. Here Y, the boundary conditions for U and R is 0. Un at Y is equal to B is again 0. This is Un at Y equal to 0 is 0. Un is a function of Y, remember. Okay, so again this is the same. Let's call this operator d squared dy squared as Ly. This operator is again self-adjoint, so Ln psi is minus mu n psi is the eigenvalue problem of this operator. Now again the problem eigenvalues are very similar. Let's call it mu m Ly psi m is mu m psi m, where mu m is nothing but m squared pi squared by b squared, and psi m's are nothing but root 2 by b, similar to what we did, sine of m pi y by b. Okay, now again we have this equation, d squared un by dy squared minus lambda n un is an. I'm going to multiply by psi m of y and integrate between 0 to b dx of the entire equation. When you do that, I'll get 0 to b psi m Ly of un dy. Okay, this is not dx, obviously, it's now dy. The integral is with respect to dy minus lambda n. This lambda n appears as such, 0 to b un of y psi m of y dy is an 0 to b psi m of y dy. Now this is again another constant. This will be a function of both an and am. Let's call this anm. So an times this constant, which is a function of m, will be designated as anm. This is definition. Okay, this is just notation. Okay, right. So now if you look at this expression, this is a self-adjoint operator, so this is 0 to b un Ly of psi m dy. Now that is nothing but lambda m, right? 0 to b un, this should be this is not lambda, the eigenvalue is minus mu m. L phi m is minus mu m psi m, right? So dy, now this is nothing but mu m. This is, I'm going to call this unm, because you are integrating un, which is a function of y, multiplied by psi m and integrated over y. So this is a function of both the indices n and m, so I'll call it minus unm, right? And then here also minus this term will become minus lambda n unm, okay, is equal to anm. Okay, okay, let's just, we can even call it an times bn. Let's call this let's call this whole thing as just bm. So just to be clear, okay, so we can solve for unm. It's an algebraic equation, because originally we had a PDE in x and y. After two Fourier transforms, after two finite Fourier transforms or Eigenfunction expansions, you are reducing the PDE has been converted to an algebraic equation, which is easily solved to get unm is minus an bm by lambda n plus mu m. Now once you know unm, you know what is un of y is nothing but m is equal to 1 to infinity unm psi m of y, and then once you know un of y, you know what is so that is nothing but m is equal to 1 to infinity. Instead of unm, I'm going to put minus a n b m is lambda n plus mu m psi m of y. Now this is un of y. Now once you know un of y, we know what is u of xy is nothing but summation n is equal to 1 to infinity un phi n of x. That's nothing but summation n is equal to 1 to infinity, right? Summation m is equal to 1 to infinity minus a n b m by lambda n plus mu m times psi m of y times phi n of x. Okay, this is the final solution to the problem using eigenfunction expansion. Always in the method of eigenfunction expansion or finite Fourier transform, the final solution will be in terms of a summation over all the eigenfunctions, where we know what ans are, what bns are. These are the coefficients expressed in terms of integrals. These are the eigenvalues of the two eigenvalue problems that we solved. Okay, these are the eigenvalues. Okay, this is how one solves. Now naturally we have chosen problems in the Cartesian geometry. When you go to other geometries like cylindrical coordinates or spherical coordinates, the eigenfunctions will not be just sines or cosines. In cylindrical coordinates, for example, in the radial direction you will have Bessel functions. If you go to spherical coordinates, you will have in the theta direction Legendre polynomials or spherical harmonics. Okay, those are details that you can pick up very easily based on the fundamental notions that you have gained after understanding the notion of eigenfunction expansions. Here you can take up any book involving these topics, including Riley and Hobson, where you will see that the method of separation of variable or eigenfunction expansion used for other coordinate systems as well, where the eigenfunctions are slightly more they may be new to you, like Bessel functions or Legendre polynomials, but the idea remains the same. There is nothing more fundamentally involved in the solution of problems in other coordinate systems other than Cartesian coordinate systems, although the details may get slightly more algebraically involved. Okay, I'll stop here and we'll continue in the next module.